We're ready to begin this morning's session, and we're going to begin with Stuart Weidenschilling, who's going to tell us about planetesimal formation, numerical modeling of particle growth, settling, and collective gas-grain interactions.
And a bit more than that, maybe. Okay.
Okay. Well, good morning. Before we begin, I would just like to mention that this month marks the 10th anniversary of the passing of Viktor Safronov. All of us who work in this area are greatly indebted to him, so much so that I thought it appropriate to quote the epitaph that appears for Sir Christopher Wren in St. Paul's Cathedral. If you seek his monument, look around you. This meeting and all of us who take part in them, and in some sense, a monument to Viktor Safronov. All right, I have as many slides as Doug Lynn had, so I've got to get on with this. I hope we can get through this. I'm not going to be talking about elegant theory. I'm going to be talking about the nitty-gritty of numerical modeling, and I have three different models that I want to talk about. One is to model the detailed structure of a particle layer in the midplane of a solar nebula. It's going to be without global turbulence, so if any of you are totally wedded to the idea of a turbulent nebula, you can sleep through the first 15 minutes or so. Then there's another model which considers coagulation of particles and settling to the central plane, the conditions that would produce such a layer in the first place. And then finally, I will say something about models for growth of planets from planetesimals and how they may be influenced by the properties of the planetesimals that we're starting with. Okay, here's my picture of the situation that we're going to be looking at, the protoplanetary disk, the nebula, the particles settling to the central plane, moving around, migrating inwards. Okay, as you heard yesterday from John Papalouizou, the gas of the solar nebula is not rotating at a Kepler rate. It's supported by internal pressure and moves a bit more slowly. Therefore, any solid bodies that are in the nebula are required to move with respect to the gas. They're trying to move in Kepler motion, but they can't generally. This causes their orbits to decay, and generally they are moving inward or towards wherever the local maximum of pressure is. And in the nebula as a whole, that's got to be towards the middle. The velocities that they are moving at depend on the size of the particles, and so in principle it would be quite easy to determine the relative velocity between any pair of particles of different sizes if they were isolated bodies. Now here is a diagram of particle velocity with respect to the gas in a typical nebula model. In general, very small particles are moving with the angular velocity of the gas, so their transverse velocity is negligible. They have a radial drift velocity, which is increasing with particle size. Very large particles here are in Kepler orbits. They're moving along at the Kepler speed, and so they face a headwind, which is of magnitude the difference between the Kepler velocity and the gas velocity. And the bigger they are, the less effect the drag has on them, and so their rate of orbital decay decreases with increasing size. And right in between those two regimes, we hit a maximum in the radial velocity, which turns out to be at exactly the magnitude of the difference between the Kepler velocity and the gas velocity, and occurs at a size for which the response time to the gas drag equals the Kepler time, which in most nebula models occurs at about 1 meter in size and doesn't depend very strongly on where you are in the nebula. Now, as I said, if you had any two particles and they were the only particles in their vicinity, it would be quite straightforward to calculate what their relative speed was and what velocity they would collide. However, when things are getting interesting in the nebula is when we have a lot of particles together in a dense array. That's how you're going to make planetesimals, perhaps. So we require the density of particles to approach or exceed that of the gas in the various models. And in that case, it's not just that the gas is affecting the particles are affecting the gas. They drag the gas with them at some rate that is no longer the simple pressure-supported value. And the relative velocities between particles of any size don't just depend on their sizes, but on everything else that's going on around them, the entire ensemble in their vicinity. So in attempting to model this, we are looking for, the shear that is induced in the gas by the particles is going to generate some turbulence, even if the nebula itself is not turbulent as a whole. And so the structure of the particle layer that results is a balance between the turbulent diffusion, which is trying to thicken the particle layer, and the vertical component of gravity, which is trying to settle it down into a thinner layer. And so we're looking for an equilibrium between that. Typically, shear-induced turbulence halts the settling process at a certain density, which is too small for gravitational instability, at least in the simple direct sense. Now, some years ago, Nakagawa and his co-workers developed a very elegant analytical solution for the coupled motions of particles and gas. The particles move inward, the gas moves outward. The entire system there of equations conserves angular momentum as it should, which means that the inward and outward flows are equal. The amount of mass flowing inward as particles is equal to the mass of gas that is moving outward. The problem with that solution, elegant as it is that it assumes everything is balanced locally. It doesn't allow for any kind of turbulent transport of momentum from one level within the particle layer to another. In fact, the solution breaks down when the flow becomes turbulent, and you have to allow for that in some way. So you still need overall balance of the mass flows and the momentum flux, but it is not conserved locally. So I'm trying to model that numerically by accounting for that. Now, one way to approach this is to look at a characteristic length called the Ekman length. This is from classic solution of fluid dynamics of a rotating disk in a viscous fluid. The Ekman length, you can express it in various ways, and I've borrowed an expression from Jeff Cuzzy for this. But you can just think of it basically as a sort of characteristic length over which the flow is going to vary in a system like this. And you can't really make the flow vary on a smaller length than this, because this is kind of how far the momentum goes and spreads. And it's sort of a characteristic length for a decay of turbulence that is generated in one place and is advected to another region. Another characteristic number that we need to keep in mind is the Richardson number. That was also mentioned yesterday. It's a measure of the stability of a stratified shear flow, where the density gradient will tend to stabilize the flow. This number defines the onset of when the energy that is derived from the shear counteracts the energy that is needed to displace an element of fluid vertically. And so you have a criterion here for the onset of turbulence. And the critical number is usually quoted as being 0.25. It's a dimensionless number. There are various statements in the literature that the number should be somewhat different, but it really doesn't matter for our purposes. And then once you get turbulence, then you have a couple of other numbers that are relevant. The Rossby number. Often it's assumed that turbulence is going to have a characteristic eddy turnover time scale equal to the Kepler time. That is generally true in weak turbulence, but Jeff Cuzzy made some arguments some time ago about if you have strongly developed turbulence in a rotating system, the frequency of turbulence gets larger by some number, which is the order of 10 to 100 or so, and that's the ratio there is the Rossby number. And then the response of particles to this turbulence, it depends on the Stokes number, where it's the characteristic response time to the drag to the eddy turnover time, where the eddy turnover time is not necessarily the Kepler time. And from that one can derive a random velocity of particles in a turbulent field. Uden and Chang did a nice, elegant model for the flow of gas in a nebular particle midplane, where they assumed a turbulent viscosity and a vertical transport of angular momentum. If the particle concentration is increasing towards the midplane, then that part of the layer is being dragged more rapidly, closer to the Kepler velocity, and the particles in the less dense layer above and below that are moving more slowly. If you have a turbulent viscosity in there, then you have a transfer of angular momentum where there's a drag exerted on the densest part in the midplane. It's losing angular momentum. It's giving that up to the slower moving particles and gas farther from the midplane. And so you have an upward flow of angular momentum and causes the central part of the particle layer to flow inward, and there's an outward flow up near the surface layer of the particle layer. They assumed, however, that the particles and the gas were perfectly coupled in their solution, and in fact that's not the case. We want to have a method to deal with larger particles and see how they interact in a situation like this. Okay, here's where it gets messy. To do a numerical model of this, I do a lot of steps, and you don't really have to try and understand all of these, even if I could make you do that in the time that I have. But what I do is I take a likely scale length for thickness of a particle layer, divide that up into a number of sublevels. At any time you start, you don't care what you put for the particle concentration there, uniform or anything else, because you're going to evolve from there. We use the Nakagawa model to compute the radial and transverse velocities of the gas due to momentum exchange between the particles and the gas. We use that to compute the Ekman length. Then we average all those velocities over the Ekman length instead of localizing them. We use that velocity shear that we've computed to compute a turbulent viscosity. We average the turbulence over the Ekman length as well, or turbulence which is generated in one region will propagate away from where it is generated, but decay over an Ekman length time distance scale. We model the eddy time scale of that turbulence according to the Rossby number and the Richardson number that we have computed. Then we plug that into the Uden and Chang solution there for the stress tensor due to the vertical shear. We add the radial velocities that come from that to the radial velocities we first determined from the Nakagawa solution, which is the particle-gas direct momentum exchange. Then we having the gas velocities, radial and transverse, we resolve the equations of motion for the particles in this moving gas. And ideally what you'd like at that point is to find that the flux is balanced. The mass flux of the particles going in equals the mass flux of the gas going out. But since we have delocalized the solution, that's not guaranteed and usually doesn't happen. You're off by some amount. So then we fudge the solution. If the particle flux is too large or too small, you nudge the velocities of the gas, the component that is produced by the particle-gas reaction, nudge that in the right direction, recalculate everything, and iterate that until you get the fluxes to balance. And that's only the part of the first time step. Then we know what the properties of the turbulence are. We compute the turbulent diffusion coefficient as well as the settling rate, and then we run off the bottom of the graph here, but what we do is we do that again and again. We iterate until it reaches a steady state solution, and things no longer change. And that is the case there where you have a perfect balance between the turbulence that is being generated by the shear and the settling rate, and everything comes to equilibrium. It takes a lot of time steps sometimes. Okay, here's the result from this. These are distributions of solid to gas mass ratio versus Z, or Z if you'd rather, at a typical location in the solar nebula. This is at 3 AU in a low mass nebula. Typically the equilibrium thickness of the layer is a few 100,000 kilometers, and the peak solid to gas mass ratio is on the order of unity or a bit less here for small particles. And it doesn't depend very much on the size of the particles. Once you get to centimeter size or below, the smaller particles settle more gently, but they also don't stir the turbulence up as much. And so they sort of more or less come to a balance here. So these curves all come more or less together. If you want to get a high density of material in the midplane of the nebula here, you have to go to decimeter or meter-sized particles, at which point the layer is starting to collapse into a thin and dense layer. Now, within each of these equilibrium solutions, you get some rather interesting flow properties. Here's for a millimeter-size particles, all monodispersed there. What happens here, I've plotted the gas velocities. This dashed line is the outward flow of the gas due to the direct exchange of momentum between the particles drifting in and the gas that they're displacing going out. But you have the shear velocity there, which is causing the upward flow of momentum from the gas down here near the midplane to the gas that's higher up, and that is this component here, and the net gas flow is their sum, which is this curve in between. And so what you have is inward flow of the gas through the lower part of this layer, and outward flow above a certain level. And the particles, which are moving not exactly with the gas but through the gas, are moving inward near the central plane, and above a certain layer they are actually being carried outward with the outward flowing gas near the top of the layer. So you've got it going in both directions at once. And this is a general feature for centimeter size or smaller particles. Here's centimeter size, and qualitatively it looks the same. The scales are different and the velocities are larger, but the general structure of the layer is similar. When we get to decimeter size, the Ekman length is a larger fraction of the thickness of the layer, and it begins to distort the velocity contours. But even here with 10 centimeter sized particles, you have this region where you have particles going inward at a velocity of several meters per second, and yet farther up near the surface of the layer you have this substantial region where particles are moving outward at comparable velocities, although there are fewer of them up here than there are down here because the higher density of particles near the midplane. And if we go to meter size, if we have a layer of nothing but meter-sized particles, they're all going to be moving inward. Their decay velocities are large in that way, but the actual velocities vary significantly with elevation. The net flow of the gas is outward, and that's this curve here, but it's really a balance between difference between two rather large components of an outward flow due to the particle gas exchange of momentum, and this curve, which has a strong inward component due to the turbulent shear. So, yes?
This accounts just for particle-gas interaction, not for the viscous evolution of the gas, right?
The nebula as a whole here is laminar, except within this layer. the viscous evolution of the gas is only that which is within the layer due to the turbulence that is being stirred up by the shear due to the particles themselves. Yeah, it's a whole other complication if you try and do this in a turbulent nebula with other sources of turbulence than this shear. Okay, and here for particles of 10 meter size, here is the radial velocity of the particles. It's essentially invariant by that time. They're not being affected much by the gas. And the outward flow of the gas is it's outward at all levels here. Well, it has some variation with height, but that's probably not too physically significant. I've done so much averaging and interpolation here that you probably shouldn't believe any little wiggles in the velocity contours. But when we go back now to the radial velocities that are due to the gas drag here, okay, the solid curve here is one that you saw before, and that's the velocity that an isolated particle would have at this size. But if we have this particular ensemble of particles with the surface density that I've assumed as plausible for this particular nebula model, I'm showing two things here. One is the collective velocity, that is the velocity of an individual particle located right there in the central plane at z equals 0 as a function of the size of the particles. Again, at each size here we have only a single size of particle. This dashed line is the mean effective velocity. That's integrated over all values of z, mass weighted. So this is basically the mass flux divided by the surface density. So the mean value at which all the mass is moving around, and of course it's always moving inward in that case. But you'll see that the peak velocity here for inward motion is kind of chopped off. It's lowered from about 50 meters a second down to about 10 meters per second here. That helps your meter size barrier a bit. It gives you a little more time for things to evolve before they're going to spiral inward too far. It may not be enough to help your theories, but it happens. Now, the whole idea of doing this was not so much to look at what a single particle size does, but also to look at what the relative velocities are between systems which have more than one particle size. And here I have a 50-50 mixture of millimeter and meter-sized particles showing the vertical distribution of them separately. The meter-sized particles are squashed down into this thin, dense layer. The millimeter-sized particles are in a much thicker layer, and there's actually very little effect that the meter-sized particles have on the structure of the thicker layer of millimeter-sized particles. They're really only affected down in this region. Here is the radial velocities of particles and gas in that particular system, where the solid line here is the meter-sized particles. The total velocity of the gas is this dashed line, and you can't distinguish the velocity of the millimeter-sized particles from the gas velocity on this scale. So what's happening is within this region, this is just the lower part here, close to the central plane from what I showed you in the previous slide. The meter-sized particles are going in, and the gas and the associated millimeter-sized particles are going outward. And you can compare well, you can look at the velocities, first of all, between these particles. And this now is a system of millimeter and meter-sized particles where I'm just varying the mass fraction here that is in the meter-sized particles. So over on the left here we have all millimeter-sized particles. Over here nothing but meter-sized, and in between we have a mixture. The relative velocities of the between the little particles and the big ones is fairly constant regardless of what you put in here, except very close to the left here, where you have only very small fraction of the mass in meter-sized particles. But even there, it's still considerably lower than the 50 meters per second that you might expect from considering isolated particles. This is the turbulent velocity that is generated in the midplane. It's a few meters per second. And that results actually in a significantly higher relative velocity between the millimeter-sized particles encountering each other than you would have without any meter-sized particles in there. They're doing the stirring. Now, it's only down in the region where the meter-sized particles are abundant, but it increases their velocities quite a bit. Okay, we can do multiple particle sizes, not a continuum, but a whole bunch of things. And this is a system where I have equal masses in millimeter, centimeter, decimeter, and meter-sized bodies, showing that the individual components are strongly stratified. And you have this contour here for the total solids abundance. But at each level, it's more or less dominated by the one size of particles. And if we had a continuum of this, it would just the size distribution would simply vary very significantly from the midplane up to the top of the layer. Okay, so the net effect of all this on the impact velocities at which particles are going to encounter each other is the small particles, which would otherwise be colliding very gently with each other. The presence of large particles will stir them up and cause them to collide at much higher speeds than they would simply from their drift velocities. And the turbulence is more intense here due to the presence of the larger bodies. The smaller particles are impacting onto the big ones, the meter-sized bodies, but instead of about 50 meters per second, which would be your kind of individual particle relative velocities, the fact that the gas has been dragged along by the bigger particles so that the delta V, the deviation from the Kepler velocity, is much smaller. It cuts that down by about a factor of 5. That would help you grow, perhaps, except that if you continue to grow and put more and more of the mass in the bigger bodies, they will start to decouple from the gas and not drag it along with them as much. And so your gas velocity in the midplane will deviate more from the Kepler velocity. It will increase its delta V, and so what small particles you have left will be hitting at higher velocities. So if there's some velocity threshold above which you can't accrete, in that case you will grow to something bigger than meter size, but it may hang up and stop before it gets beyond a certain point. So the growth may be limited by erosion, and in fact with the next simulations that I'll show you a little bit later, we do have cases like that. But looking at the overall drift velocity, here again is a system here with millimeter and meter-sized particles. And the drift velocity for the meter-sized particles is always negative, that is, they're going inward toward the sun. And yet, when we throw in some meter-sized particles, the mass-weighted drift velocity, the net flow of the millimeter-sized particles is outward. What's happening here is in the much thicker layer of millimeter-sized particles, most of them are drifting inward slowly, but within the dense layer of meter-sized particles, the outflow of the gas is so rapid that the particles, the little particles that are being carried along with the gas, are actually have a higher mass flow outward than the entire rest of the layer drifting inward. So just about any time you have a significant number of big particles present, the total mass flux is inward, but that's all by the big particles, and the little particles are going outward. So you may have some sort of radial mixing going on as a result of that. Okay, how does all this vary with surface density? Suppose we have a nebula, and instead of using the nominal amount of mass there, we add some to it or take some away. I think Andy Uden will be saying something more about streaming instabilities, but the basic idea there is if you add mass to some region, if that slows down the drift rate due to the collective effects, then mass will tend to pile up there, and other material coming in will catch up with it and increase the surface density. This can lead to an instability that will give you a much higher density in some locations and lower density in others. This might lead to planetesimal formation. However, for nominal cosmic abundances, in this particular case, the surface density would be about here, between 2 and 3 in this model. Depleting the region in particles doesn't really speed up the remaining particles very much, and in fact, in order to get a significant effect in the mean drift velocity, you have to increase this by several times before these curves begin to turn over. So you have a much more effect if you can make things up to meter-sized particles. You might have a better chance of developing a streaming instability then, rather than with millimeter-sized particles. But it does complicate things a bit. And if we have a mixture of particles of different sizes going on, some are going to be going in, some are going to be going out. I'm not sure what this will do for streaming instabilities. If we do manage to increase the surface density in some locale over the nominal cosmic abundance, it begins to behave a little bit strangely. Here is for millimeter-sized particles and the nominal solution right here. If we add material so that we have, say, 4 times as much surface density as we normally would start with, what we get is a thicker layer and a higher concentration at all levels down to the midplane. If we continue to add solids, the system overloads and it becomes thinner again up here, and more material is concentrated down into the midplane and builds up into this strong peak here. You get a sort of a singularity where the turbulence is not sufficient now to be lofting all of the particles that you have there. You simply have too much mass to be stirred up. This actually is a pretty good match to an analytic solution that Sakia came up with a few years ago, which makes me reasonably comfortable that the numerical model is reflecting something physically realistic here. Okay, so to summarize the first half of my talk here with this particular model, when you're computing the relative velocity between particles, you can't just consider the individual particles, but the entire ensemble, their environment in which they are colliding with each other. You can get complicated flows both inward and outward at different levels, even for a single size, and if you have multiple sizes, you will have even more complex flows and inward and outward flows of particles of different sizes. And again, it's rather hard to have small particles drifting in because there's a lot of outward flow produced by even a small mass fraction of large particles because they are spiraling in fast enough to force the small ones out. Okay, that was the first model. 2 to go. Okay, this one will be a little bit more brief. This is stuff I did quite some time ago, though I did a few new calculations for this particular meeting. And I have a model that now doesn't compute in such detail the structure of the particle layer, but it does allow for coagulation of particles when they're colliding, and it looks at the structure all the way through the thickness of the nebula, from the central plane up to 2 scale heights from the central plane, two scale heights of the gas. So that's quite a bit. It looks at this in a series of layers with finer resolution near the central plane where you need to know the distribution of particles. And it looks at size distribution of particles from micron size on up to kilometers if you can grow things that big. It also considers that the small particles have a fractal relationship of density to size. And it looks at all of the possible sources of relative velocities, differential settling, thermal Brownian coagulation, turbulence. You can plug in an alpha if you like on that. And for big things, I kind of do a crude approximation of gravitational stirring for things that are sufficiently large using a Safronov number, and increase gravitational cross-section for the largest bodies if you do make kilometer-sized things. The impact outcomes that I assume for this model are very much simplified compared to what Jürgen is going to tell you in the next talk, and may be totally wrong in that, but we consider both disruption if bodies of comparable size collide with each other. And simply look at the energy density, and if that's exceeded, you're going to break this thing up into small fragments. If a small particle hits a much larger one, I make the assumption that it buries itself in the target, but kicks out some ejecta from sort of a crater that it would make in that case, and that the mass ejected is proportional to the impact energy. And what that does then is it gives you a proportionality such that there's a critical velocity above which you will lose more mass than comes in. This may or may not be a reasonable approximation to what experiments give us. But for this particular model, at least, then there is a transition then from net gain to erosion when small particles are hitting larger particles. There's a critical velocity for that. If we start this model, and this is at 1 AU now, starting with micron-sized particles uniformly distributed through the gas up to 2 scale heights. If we assume perfect sticking, this is what would happen. This is the size distribution in the central plane now, at z equals 0. What happens first is we have Brownian coagulation, completely depletes the really small population. And in 1,000 years, not much has settled to the central plane, so you don't have as much mass here. But then, over the next couple of thousand orbital periods, the material that was coagulating farther up all settles down into the central plane, or a significant amount of it does, I should say, and it greatly augments the mass here. And then you grow things, and with perfect sticking, of course, you have no problems making planetesimals. And we grow things up to tens of kilometers in a few thousand orbital periods. And interestingly, this sub-meter size material is almost completely depleted. The reason being it's all being swept up by the big things. So you don't have anything that looks like a power law here at all. If we try and put in some more realistic strengths for these bodies, okay. The initial evolution, again, is Brownian coagulation that depletes the micron-sized particles. But then as you grow things to bigger than meter size, for this particular set of parameters, things would shatter if they collided with bodies of comparable size, collided at a few meters per second. But the erosion parameter is such that the critical balance between net gain and mass loss is at 10 meters per second. And it turns out that for these parameters, that's exceeded at somewhat around meter-sized bodies, even with the collective interactions going on. And so what happens is, after a while, it completely stalls. You grow things to roughly meter size, nothing gets bigger, because anytime anything gets bigger, it starts eroding instead of gaining. But you have this power law tail of small particles that's continually created by the collisions that are eroding the bigger ones. If we change the parameters a bit and say it's a little bit more difficult to erode things, maybe they get buried more easily in their targets, and this is now raised up to a few tens of meters per second. That's greater than the typical impact velocities, and it goes right ahead and it grows things, and in a few thousand years you'll have kilometer size or larger planetesimals. This really depends. Well, let's see. Okay, getting ahead of myself. Okay, here I put in an alpha of 10 to the minus 5, which is pretty pitiful by most people's standards, but gives you a turbulent velocity of a few meters per second. Even though the impact strength is rather low, 10 to the 5 ergs per gram, and the shattering velocity is low, therefore, I've picked the erosion parameters such that you still need a fairly high impact velocity to erode these things. And this, even though we do have a little bit of turbulence in here, it doesn't inhibit the growth. And again, after a few thousand orbital periods, we are growing things to kilometer size or bigger. This is really the aerodynamic contribution, and out here, when we start to grow things bigger, we're putting in the gravitational cross-section, so we're already beginning gravitational coagulation in that case. Even if the impact strength is very low for comparable sized bodies hitting each other here, 10 to the 4 ergs per gram, which means if two equal sized bodies hit at a couple of meters per second, they would be totally shattered. We can still get growth as long as we're not having erosion by the little things hitting the big things. So that seems to be more of the growth limiting factor, is what happens when a little particle hits a much bigger one. What is a critical velocity? Yep.
Stu, I'm having trouble following where the mass is, because the first curve seems lower
Yes.
all the time.
Okay, as I said at the beginning of this is the distribution in the central plane. This is the result of a calculation where I'm calculating all the way up to 2 scale heights. So at time 0, most of your mass isn't even there, so it's not on these curves. And the increase in mass is the stuff that's fallen down from farther up as it coagulated and settled. So the mass is not conserved here. It's being added to, although after, again, a few thousand orbital periods, most of the mass is down there in the central plane, and the rate at which it's being augmented is much lower. Okay, so the bottom line for this kind of simulation is, if nothing else was stopping it, you would grow things quite big, and material would reach the central plane in a few thousand orbital periods. I showed you at 1 AU, and it's sort of comparable. Even if you go out to 30 AU, it's a few thousand orbital periods out there, although the periods are longer. Growth will be halted if you make a transition from net gain to net erosion in the collisions of little things hitting big ones. Even for very low impact strengths, you could still have growth. It's the erosion that seems to be the critical factor. Therefore, I think this is the region that experimentalists should be paying most attention to for models that involve formation of planetesimals by collisional interactions. Okay, now on to the third part.
May I ask a question?
Yes.
Do these models include also the relative velocities between large and small bodies due to radial drift? Or
Yes. Yes, that's all in there. And it also includes turbulent velocities when turbulence is generated by the shear, as well as if I put in an alpha, that's an additional turbulent velocity. So that's all in the model. Okay, on to the third simulation. Now Morby is going to be talking about this topic today in much more detail. I don't want to steal all his thunder, but I'll try and give you a brief recapitulation here. Now, usually people like to think of kilometer-sized planetesimals. There's no real reason for doing that, except that the mindset for saying planetesimals were kilometer-sized goes back, I guess, to Goldreich and Ward, which is so 1970s. And ever since then, people have sort of started with kilometer-sized objects when they're doing accretion simulations, and they talk about that as being a typical planetesimal size, even though the Goldreich-Ward model is no longer considered particularly valid. So is there any evidence that we actually have that could tell us something about what planetesimals were like, or has it all been erased? And Morby and the gang at Swery have argued that the asteroid belt may preserve some information about the original size distribution. Now, it's gone through a lot since then, since you first made planetesimals in the asteroid belt. And the dynamical history is you accreted really large embryos, then they were depleted by scattering into resonance with Jupiter, and then followed by more than 4 giga-years of collisional evolution. And yet there may still be some trace remaining, at least if you believe the guys at Southwest Research. Okay, this just recapitulate some of this. The present-day size distribution of the asteroids, I'll show you that in a minute, shows an excess of 100 kilometer or so size bodies relative to what you would consider to be a collisional equilibrium power law. Another constraint that has been invoked, and Morby will be saying more about this, is that Vesta still has a more or less intact basaltic crust. If you had too many somewhat smaller size asteroids out there over billions of years, they would have destroyed this crust if you had too many of them before the depletion of the belt was completed. And so you want to ask, could you produce something that looked like this, starting with planetesimals? And if so, what planetesimals would it take to do that? Okay, here's the present-day asteroid belt size distribution. You see it's not a simple power law, and you have this excess here in the 100 kilometer range. These other curves are those that were suggested by Botke et al. As possible initial sizes before you depleted, after we depleted the belt, but before you had 4 billion years of collisional evolution. So all these small things here are fragments of some of the things that were originally in this size range. So how do you get an excess of 100 kilometer bodies and a relative lack of things smaller than that? Well, I put this into gravitational accretion code. This is the PSI planet building code. It's a multi-zone code where we put things into zones of semi-major axis. For these simulations, I use 15 zones from 2 to 3.5 AU. It computes the collision rates of bodies in overlapping orbits, the impact rates and velocities. It has gravitational scattering evolution, and it has impact outcomes of accretion, cratering, or disruption depending on the impact energy. And it keeps track of the size of bodies in logarithmic size bins, and if things get ground down too small, the fragments are lost from the system. Okay, so here's a typical simulation done with that, starting with the canonical kilometer-sized planetesimals. This is the cumulative distribution versus diameter, and at time 0, this was kilometer-sized. We let this evolve for several million years, which is the time when presumably the dynamical depletion of the asteroid region began after you'd formed Jupiter. And you form this kind of wavy size distribution, but instead of having a hump at 100 kilometers, you have a lack of bodies there, and you have far too many at about 10 kilometers in size. So this doesn't work. Spectacularly, it doesn't work. It's very bad. If we started with nothing but 100 kilometer bodies, so that was our original planetesimal size, the evolution is something like this. You got this bump at 100 kilometers because that's what you started with really, but the rate of runaway growth of planetary embryos is much slower if you only started with big bodies, and you end up not making enough large things the size of Ceres or big enough embryos to do the dynamical scattering. So this doesn't work either. So we try to compromise and say, well, what if I started with 10 kilometers? Is that the original size of planetesimals? Well, not really. It looks better than the other ones. You've got sort of a bump here at 100 kilometers or so. You've made some big things. You really still have too many things in the 10 kilometer size range. It would be very unlikely for Vesta to look like it is now if you had that many of them. And possibly we could play around with this and have some initial size distribution in the range of, I don't know, a few to a few tens of kilometers. That might be a better fit, but it doesn't look very good. Then I said to myself, okay, aerodynamic accretion driven by gas drag doesn't even make things as big as kilometer size. It sort of runs out of gas in a way when you get up to things that are about 100 meters or so in size. So what would happen if we started with 100 meter size planetesimals instead of kilometer size or bigger? Well, I expected when I did this that it would be a spectacularly bad fit, and we could maybe finally drive a stake through the heart of the binary collisional coagulation formation mechanism for planetesimals. And when I did this, this is what popped out of the simulation on the first time I did this. We've got enough big things here to do the dynamical stirring. We produced a excess of 100 kilometer sized bodies and a lack of 10 kilometer sized bodies. It all looks like it's got all the features you need for this. So it was kind of scary, actually. And I have to admit, I'm not really sure yet why it does this. To paraphrase something that Doug Lynn has said yesterday, I could say I'm seldom wrong, but often in doubt. Okay, so starting with 100-meter sized bodies here, and a huge number of them, what's happened here is somehow the accretion process has produced this wavy size distribution. It is not a matter of collisional fragmentation doing this. I've tried this without fragmentation, and it still gets something rather similar to this. It has something to do with the way the code is looking at the rate of runaway growth, the balance between gravitational stirring and the collisional cross sections as it's evolving when you have the mass distribution dominated by much smaller stuff. I still don't know for sure if this is a subtle defect in the logic of the code or if this is a real effect. So I'll have to get back to you on that. But it looks like a rather promising result considering I hadn't tried to bias this in any way. I just plugged it in and this is what came out of the model. What's happening here is since you have a lot of mass in really small bodies, they're easily broken up, and in this particular simulation they're simply lost. If they get ground down to 10 meters or so in size, all the fragments are lost, and about half of the starting mass has ended up lost from this particular simulation. So this is a work in progress, and I'm still trying a bunch of things. Some of them are running on the CPUs back in Tucson even as I speak here. There are things to do to look at. Vary the initial size a bit from the 100 meters. Have some dispersion of sizes about that mean, since you don't really want to have everything exactly the same. What happens if the planetesimals are added over some interval rather than instantaneously? And things are evolving so rapidly early on that you wonder that even a time interval of a few thousand years to produce these things might make some difference. I'm not sure yet. And is all the material that's ground down into little fragments, or so darn much of it, can we really throw that away, or do we get something different if we recycle it all into new planetesimals during this process? So the bottom line on this is, well, I haven't been able to kill the idea of starting planetesimals very small sizes. This idea still seems to be viable from this standpoint at least. So maybe planetesimals started big, as Morby will be telling you later, or maybe they started really small. And we will find out, I hope. That's all. Thank you.
Okay, thank you very much. Are there more questions? Jack?
Do you have any plots, or can you describe the curves of those 100-meter simulations at smaller times than 1 million years?
Mm-hmm. I've done that. I don't think I have them on here now, or if I did, I couldn't find them. I've looked at that, and yes, this general configuration actually is established at much shorter time scales, within like 100,000 years or so from starting the simulation. Runaway growth is so rapid when you start with really small bodies that you've even grown the things up to like 10,000 kilometer size in that time scale, which is much less than 1 million years. And they've produced basically that entire curvy size distribution very early on. The only thing that happens after that is you continually deplete the really small stuff due to collisions.
Do you produce the 100-kilometer region bump before you have those runaways embryos getting very large, or later?
Yeah, that happens first before you've grown things bigger than, say, 1,000 kilometers or bigger.
So do you get at that point, do you have something like what Morby has, except you have a bunch of small stuff and then you have this distribution kind of peaked around 100 meters.
You mean around 100
100
kilometers?
kilometers, yes.
Yeah.
Sorry.
I don't know. Morby and I will have to discuss that a little bit more detail, I think, to figure that out. I'm not sure if these are compatible or not, but it's an interesting thought.
Richard?
Stuart, I was just wondering if you could expand a little bit about what goes into that final model you showed. I mean, is that occurring in the presence of gas drag? Is Jupiter in there?
Jupiter is not in there. This is presumably before there was a Jupiter. Gas drag is in there, although that doesn't seem to be particularly vital to the outcome. In this first simulation that I did, I have gas drag doing some damping of the eccentricities and inclinations, which is most effective for the smallest bodies, but it doesn't do a whole lot of damping on that time scale. When you're considering really small things, actually smaller than 100 meters or so, you actually have to start thinking about the effects of gas drag on relative velocities, because that's becoming comparable to the gravitational stirring velocities that you're getting in bodies that size too. And I've been running simulations since then that include that. So the very smallest bodies, the relative velocities don't keep dropping as they get below a certain size. They may actually go up again. But again, I don't see any strong effect of putting that in at this point.
Well, I guess a long-term test of this model is to actually run it for 4.5 gigayears, isn't it? In the presence of Jupiter and whatever else needs to go in there.
Well,
to see how well you actually reproduce today's asteroid belt size distribution.
Well, in some ways that's already been done by Morby and his colleagues at Southwest Research Institute. They go from there and have evolved it through all the dynamical depletion and the subsequent collisional evolution. So I don't think I actually have to do that myself. That's been done. I just have to get it to this far, to that particular size distribution, and the rest of it's all been solved. Right, Morby?
A question myself on the second model, you gave the shuttle velocity and the erosion velocity of the order of few meters per second.
Yeah.
But the sizes you were considering, the escape velocity is only a few centimeters per second. So what happens in between a few centimeters per second, a few meters per second? Do particles stick somehow by magic forces of the gravity?
Yes, it has to be done by magical force. It's not gravitational in that regime, because the velocities that are induced by gas drag are much bigger than any escape velocities. So any sticking mechanisms in that size regime have to be non-gravitational, surface forces or mechanical interlocking or
even
something.
At the 100-meter level.
That's about when you start beginning to get to where gravitation is going to be significant. But I'm sure Jürgen will have something to say about those sticking forces and such.
So about this model again, are your initial speeds comparable for the small bodies? Are they comparable to the escape speed from 100-kilometer bodies?
What, here?
Yeah.
No, when I'm starting with nothing but 100-meter sized bodies, the initial velocities are comparable to the escape velocities of the 100-meter sized bodies. It's a very quiescent system at that point. What happens then is, as you start to grow things, that's one of the things that triggers this extremely rapid runaway that forms this size distribution early on. But then you start making those bigger things, then the gravitational stirring is increasing the velocities as you go along. So the eccentricities and inclinations are going up very quickly in the early stages of this growth.
You just mentioned that without fragmentation, the things would not change much. Could you please explain what the differences were?
Okay.
It might have been subtle.
Yeah. Well, if there's no fragmentation, you don't get this depletion here. You keep more of the small stuff, and this curve, up to sizes of maybe 10 kilometers or so, you have many more bodies than you would otherwise. But even in a case where I don't have fragmentation, I still find this kind of wavy structure there with a hump there around 100 kilometers. So whatever the code is doing, it's doing this primarily by the coagulation rate and the collisional cross sections, I think, in that size regime.
Richard?
Third question. Do you have any turbulent stirring in this one?
No,
Not at all.
none at all.
What would happen if you put in an alpha 10 to the minus 5 or 10 to the minus 4?
I'm actually running models that include that now. Actually, we call it gamma. That's the same parameter that Morby is doing, which is not aerodynamic turbulent stirring. It's the density fluctuations that would result from turbulence. So I'm running models now that include that as well to see if that makes a difference, but I don't have those results yet.
Louis?
Can you go back to Model 2 for a second? Could you tell me when you transition from shattering to eroding, or the eroding criteria? What mass ratio? I'm just a little bit confused about why these two criteria are not connected to each other. So if you're talking about, I certainly understand why you expect, for example, catastrophic disruption to be velocity dependent and mass ratio dependent. I understand that, but why can, maybe I misunderstood, can you vary these, are you just varying the shattering criteria and the cratering criteria, or critical cratering criteria, independently of each other?
Yeah, there's limits to how you can vary them independently. In fact, the original formulation I used was, I said you had you used the cratering erosion efficiency up to a certain point, and you only can make a crater that's so big, and then after that you would have shattering.
Yeah.
And so in that sense, you really can't vary them totally independently. You can do that within some range like this, but you're sort of implicitly then saying what's the biggest crater before you shatter.
I see. But I mean, what mass ratio of impactor to target?
Okay,
Would
well,
you
it can
transition
be anything. We have a large dynamic range of sizes here, and what it's looking at is when you do this, you're looking at the specific energy input to the target, the collision. So it's not velocity; it's the total energy that's put in. So it depends on the mass and the velocity of the projectile.
Okay, I think we'll move to the next talk now. Let's thank Stuart again.